this one. Okay, so if you did look at number 1, and you see it's sine cubed of x, it might be handy to rewrite that, just so you can kind of see what's really happening. It's integral of sine of x quantity cubed dx. And maybe if you rewrite it like that, you can see the issue that's brought up here, right? Because this almost goes, this is kind of like Caroline when you were talking about the one in the WebAssembly. It's like, I tried to use the chain rule, but like the inside and the outside, like nothing was really matching. This is kind of the same thing, right? You look at it and you're like, well, it's obviously a composite. The inside is sine and the outside is cubed. And so normally we'd be like, hey, where's the derivative of the inside? The derivative of the inside is cosine. It should be it's not in there. This is not going to work with kind of those standard to mess up the chain rule / u substitution type techniques. So here's what we do with this. I will say, I kind of made a call on this. I'm sure you're not unhappy with this. There's really 2 distinctly different patterns when it comes to this sort of question. If the power on the trig function is odd, you do one thing. If the power is even, you do something else. And I chose to just do the odd version. But just know that if it was sine to the 4th, you'd have to do something different. Okay? And we can kind of talk about that a little bit if you want. But in any case, here's what you do if the power on the trig function, in this case sine, is odd. You split it up in such a way that you end up with a squared. So you'd get sine of x to the 1st times sine squared of x dx. So all I'm basically saying is that something cubed is the same thing as something times that thing squared, right? Splitting it up a little bit. What on earth would that accomplish in reality?
Well, you can use the trig identity.
Now we can use that trig identity, the Pythagorean identity, right? So sine squared is also known as?
1 minus cosine squared.
There you go. Yeah, so we could rewrite this now to be sine of x, parentheses, 1 minus cosine squared. Okay, well, I mean, I don't know. So far it looks like, I mean, to the untrained eye, they'd look at this and be like, whoa, okay, so you've made it more complicated, right? You've taken it from like a pretty simple looking thing, and now it's just like only gotten bigger and bigger with each step, which is true. But it's getting more useful as we go. So any thoughts on what I could do next? Because right now, it's like, I think I would distribute. Yeah, so integral of sine times 1 is just sine minus sine of x times cosine squared of x dx. And this still might not be all that obvious, perhaps, like what needs to happen. What are you allowed to do if you're doing the integral of a sum or a difference? Like this, right? It's like split it up. And I think if we split it up, we're going to see something kind of happen for us. So integral of sine minus integral of sine of x cosine squared dx. So the first thing that I notice is the first integral is super easy, right? That's kind of nice. So I'm just going to write integral of sine is
Negative cosine x.
negative cosine, yep, so negative cosine of x minus, what about the other one? The other one kind of is like, I don't know, do you see there's a pattern there?
1/6 cosine x.
You can do a substitution, say again?
Is it 1/6 cosine x to the 3rd?
1/6.
I don't know. 1/3.
Should be, I think.
Got
Hey guys, check this out. Let me show you.
magic.
Let's see if we can explain the magic a little bit. McKenna, watch really carefully. I'm gonna erase the squared on cosine, and I'm gonna rewrite it like
I know what.
that, right? So when you rewrite it like that, now we're back to the composite thing, right? We've got cosine of x inside of squared, and so in a case like this, you would say, is the derivative of the inside the outside? Real close, right? What's the derivative of cosine? Negative sign. So I want there to be a negative here. So then I got to put a negative out there, which makes that a plus, which makes this a plus. That make sense? And now, it's really just a power rule, right? The negative sign of x just goes back inside where it came from, and you just go plus 1 to the exponent, right? You just use a power rule. That make sense? So you'd get plus cosine of x quantity cubed divided by 3, but I'd probably just put 1/3 out front. And then don't forget the plus c. After all that, don't forget the plus c. Okay, so of course you can check this by differentiating. You want to check it real quick?
Alright.
It's not that bad. Let's do a quick check. Come on. So let's just go ddx of what we've got right there. So what's ddx of negative cosine x?
Sine of x.
Yep, positive sine of x. Okay. And then ddx of that other term?
Oh.
1/3 cosine.
Well, 3 gets to come
I'm
down.
looking at the wrong line. The
Cosine
sine
x
cosine
squared.
x squared.
Cosine of x squared times
Sine.
negative sign, right?
Negative sine.
So it'd be minus cosine squared times sine. Yeah, does this look like our original?
It looks like that
So
one.
that's closer.
Not yet. Yeah, couldn't we factor out the sine? Sine of x, 1 minus cosine squared. Oh my gosh, look at that. What's 1 minus cosine squared?
Sine.
So sine of x times sine squared of x is sine cubed of x, and so maybe we just sort of proved that that actually did work. Okay. We don't often check like that. That's kind of fun. Do you guys have any questions? Okay, so here's the rule of thumb. If you've got an integrand and you've got cosines and or sines in there, and they've got powers on them, if one of them is like an odd, like a bigger than 1 odd, then split that one up into first power and squared power, okay? Once you've done that, use the Pythagorean identity, do some distribution, kind of assess where you are, probably going to be some reverse chain rule situations there. So if you guys can handle that, let's see if you guys can do number 2. Number 2 is a little more complicated, but the principle is exactly the same. So take a few minutes, work that one over. Oh. We'd want to split this up. So I'd go integral of cosine times cosine squared, and then we just leave that sine to the 4th alone. So this is kind of the pattern here. If one of them is odd, the other one's even. We just leave the even one alone, and we mess around kind of with the odd one. Whoops, it's frozen. Let me fix that. So then once you have that split up, then we can replace cosine squared with the Pythagorean identity, which would be 1 minus sine squared. And so we would have integral of cosine times 1 minus sine squared times sine to the 4th and dx. And then we just distribute both of them. So we'll end up with integral of cosine of x times sine to the 4th of x minus cosine of x sine to the 6th, like so. You can kind of see this is like laid out pretty nicely, right? You've got 2 like chain rules, right? Where you can see like one of them is a composite factor, the other one is the derivative of the inside. So if you want to, you probably could just do it from there, but perhaps it'd be easier to split it up. So I will do that. So it's this minus that. And now we can just kind of look at them separately. But in both cases, isn't the derivative of the inside already in the integrand, right? There's no adjustments needed, or use substitution is not going to yield any big changes. So I think what we can do then is from right here, go straight into the first one. I think would be 1/5 sine to the 5th using the power rule. And then the other one would be minus 1/7 sine to the 7th. And then plus c. Make sense? We don't have to do it on this one, but we could always differentiate that and try to match it with the original integrand. Oop, that's supposed to be a 5, right? Yeah, there we go. And it should, maybe with a few identities thrown in there, should work out okay. Can I take just like 2 seconds and at least give you, I kind of feel bad about the even thing. Maybe you care, maybe you don't care. Let me at least just tell you genre of our class where the only time I'd ever assess you on this is somewhere in chapter 8, quizzes or tests, but never beyond that, is trig substitution. And before we talk about kind of the little couple sentences up there above, take a look at that integral. Whew. Right? You look at that and you're just like, wow, doesn't it sort of look like an arc sine, sort of? But with that extra x squared. Yeah, I mean, like, again, you guys all are of the trained eye. You're not the untrained eye. I mean, you look at that and you quickly are like, whoa, oh man. Not only is it sort of look like an arc sine, now it's not really an arc sine. It's way more complicated than that because of the x squared. What do I do, right? And so, no matter what you tried, whether it would be ln or arc sine or arctan or anything else at this point, you would run into a major issue. And so our new technique to deal with something like this is kind of outlined up above. We're only going to focus on one of the 3 ways that this could be substituted. We're going to be using sine for our substitution. So when the integrand involves the square root of a squared minus u squared, and hopefully that sort of looks familiar, right? Because that kind of goes with arc sine, right? Kind of, sort of. And so if you've got an integrand that involves that, then perhaps using u equals a sine theta will get us to a good place. Okay, these are challenging. This will kind of push your understandings with trigonometry and integrals, and it'll all work out. It should, hopefully. We've got a good question there. But that's what we're going to use. So I guess I'll scroll right about there. So here's what we're going to do. We're going to look at this and we're going to say, number 1, lots going on there. It's not going to fit the normal stuff. That was like my throw up sound, like, oh, what are we going to do with this, right? And then the next thing you would do, I'm trying to approach this from like you're on a quiz or test, and you just come across this. Once you realize, okay, this is not normal, the next thing I'd hope you'd see is that right there. You'd say it's square root of 9 minus x squared, and that is kind of that pattern, right? The square root of some constant squared minus some function squared. And so maybe you would be led to believe, okay, I'm going to have to use what's called trigonometric substitution. It does look kind of ugly on the front end, but the technique that we navigate through is beautiful. It really is. So we're going to use a substitution here, a u substitution, where u equals a sine theta. So let's be clear about what our u is. Wouldn't our u, like as far as trying to figure that out, we got a u right here. For this particular question, what would you say the u would be? I've highlighted them for you. I don't think u would be x squared. I think u would be x, right? Because u squared goes with x squared. So I'd say u is x. So I'd come over here and say, for my substitution, x equals, what's my a value? 3. Okay, so we're going to go 3 sine of theta. Now, why on earth are we taking something that's like happily x's, and we're not only going to introduce trig functions, we're going to introduce a theta. Yikes. We're not doing this just for kicks, just to see if we can do it. What we want to do is we want to get to a place where we can use a trig identity to simplify it significantly. And we'll end up going back to the x's in the end, but we've got to get to a place where we can use a trig identity, otherwise this just won't work. So it's more of a practical idea of how is this actually going to work. Okay, so that's going to be the case. Anytime we do substitution, we also look for a dx. So what is our dx for this one?
3 cosine theta?
Yep, 3 cosine theta d theta. Okay, and once I've done that, I'm going to go in there and start trying to substitute a little bit. So I'm going to replace my dx with 3 cosine of theta d theta. Right, so I've just basically substituted that in for that. We just found out a second ago that they're equal to each other. Then I'm going to do my substitution from the front end, right? We know that x equals 3 sine theta, so it's x squared, so that would be 9 sine squared of theta times the square root of 9 minus 9 sine squared of theta. So kind of like that other one we did, somebody, the untrained eye, or maybe even to the trained eye, could look at this and say, what have you done? You have made this way more difficult than it was before. But the truth is, we haven't, and here's where it's about to get a lot easier. Look what's in the square root. Maybe we should get the 9s out. You'd see a little bit easier. So if we wrote it as integral 3 cosine theta d theta over 9 sine squared of theta, would it be okay if I just factored out the 9 and square rooted it? So it looked like this. It would be times 3 square root of 1 minus sine squared. Does that make sense? Factored out the 9, square rooted it, square root of 9 is 3. Now what do you see in the radical? Isn't that the Pythagorean identity? Isn't that kind of the theme of our day, is like the Pythagorean identities? 1 minus sine squared. It is the difference of squares, but it's also cosine squared using the Pythagorean identity. And furthermore, what's the square root of cosine squared? Cosine, yeah. So there's more beautiful stuff that's about to happen. 3 cosine of theta, d theta, that's in the top. Down below I've still got 9 sine squared of theta, but now it's 3 cosine of theta. Do you see the cancellation? So cosine theta, 3 cancels with cosine theta and 3. And I don't know how hard this ending will end up being for you. I'm sure you can handle it. Let's get the 9 out of there. So it'd be 1/9 integral, and really it's just 1 over sine squared theta times d theta. Anybody a little fearful that this might end up being like the thing we've got up on the board? Let's manipulate this a little bit. What's 1 over sine squared? Cosecant squared, yes. Okay, so 1/9 integral cosecant squared theta d theta. Integral of cosecant squared theta. Who knew? Could we do that? There you go. Let's turn it into this and balance it out by doing that. Isn't the derivative of cotangent negative cosecant squared? So the antiderivative of negative cosecant squared would have to be cotangent. So negative 1/9 cotangent theta plus c. We're still not done though. We got to get back to x's, don't we? So, does anybody have any idea on how I could get this back to x's? And right now it's in terms of theta, and we've accomplished a lot. I mean, we've done a lot of good work, no doubt. And please don't tell me erase the theta and put an x. Solve what for x?
Theta for x.
In which equation?
The x equals 3 sine theta.
Okay, so I agree that we want to use this, and what do you want to do with that?
Just find theta in terms of x.
Okay, I can live with that. I would approach it slightly differently, but we are definitely going to use that. What I think I would do, and this might be kind of what you're talking about, I would divide both sides by 3, so I'd get x over 3 equals sine of theta. I don't think I'd do inverse sine necessarily. I think I'd leave it like that and I'd build a triangle.
Okay.
Because all I really have to do, I don't ever have to really figure out what theta is. I just need to do the cotangent of it. So if I could put it inside the right triangle with the right angles and side links and all that stuff, I could just do the cotangent of it and I'd be done. That make sense? I'm going to build a triangle based on that substitution. Let's try that again. So I'm going to say theta is there. So sine of theta would be opposite over hypotenuse. So I'd say the opposite side would be x. Hypotenuse is 3. I'm supposed to do the cotangent of that angle. So cotangent would be adjacent over opposite. What am I missing? Don't have the adjacent. So what could I use to find that? Pythagorean theorem. What is it?
9 minus x squared.
and we square root that.
Yep.
Okay, so now we got it. So what I need to do now is take the cotangent of that angle, which has only x's in it. Once I've accomplished that, I'm done. So I'll do that up here. Adjacent over opposite plus c. Whew, a lot going on in there, right? That's like, big boy and big girl math for you, for high school folks for sure. I mean, that's definitely a lot going on. Do you understand the concept? Do you understand why we went to theta? Like, can you explain it in a nutshell? Like, there's really only one reason we went to theta. Do you know what it is? It wasn't to be fancy, although it is. What's the one reason? Why would we go through all that pain and suffering with thetas and sines and cosines? You got to use the trig identities. Yeah, the Pythagorean identity. So it really comes down to dealing with this radical, and the way that we could deal with that radical is this process that I'm highlighting here, kind of finishing with that, being able to say, all right, 1 minus sine squared is cosine squared, takes it from two terms. I mean, here's like the thing we'd be trying to avoid. Here is what the very inexperienced math student would do. They would look at this that I'm putting in an orange box, and they'd be like, oh, look, square root of 9 minus x squared, that's 3 minus x, right? Pretty terrifying math. That's really, really bad. We can't really do that, and so what we do is we try to take that binomial and turn it into a monomial. The way that you can do that is to use a Pythagorean identity, right? You can go from 1 minus sine squared, which is still a binomial, turn it into cosine squared, which is a monomial. You can square root a cosine squared and just get a cosine. So let me erase that before somebody sees it. Get it off the video real quick. So that's the whole reason that we go to sines and cosines and thetas, but then we do have to come back around to them because it needs to be in terms of x, because that's how it started. So just so you know, I think, forgive me for not looking this up ahead of time. I'm pretty sure one of the other patterns involves u equaling like a secant of theta. And I'm spacing out the other one. I don't know. It's one of the other trig functions. So yeah, Darian.
So would it be acceptable to write -1/9 cotangent of the inverse sine of?
Oh, yeah, sure. Inverse. So it'd be cotangent of the inverse sine of x over 3.
Yeah.
So numerically, that's correct.
And that doesn't look good.
Yeah, it doesn't look good. Yeah, for sure. I can say for sure that, from a college perspective, like from the college, like Shake the Rust Off class I took this summer, they would never take that.
Okay.
They would want it to be simplified down to, something like that.
Okay.
If there was like if this were an AP calculus topic, they very well could, because they're not big on making you simplify.
Right.
So, yeah, at least the college teacher that I had, so like this exact type of topic was in the like the calc. So I took Calc 4 or DiffyQ / linear algebra. That was my remember how to do this. Well, it's called DiffyQ. So there was like the first chapter was the do you remember Calc 1, 2, 3, right? So there was, I'm sure, some question like this on there, and like this particular professor was like very strict. He wanted you to like simplify things. So you just have to base that on the professor. But my experience from way back and my most recent experience was you'd probably have to simplify. Yeah. Yep. Okay. Any questions at all? Anything? McKenna.
Why did you choose to be a teacher?
Why did I choose to be a teacher?
Yeah.
As a 10th grader, I felt called by God to do it.
Really?
Pretty simple. Yep.
More.
I was like,
That's pretty up there. There you go.
I was like super stressed, as like I don't know, so like I would say like a 8th, 9th, 10th grader, I was pretty stressed about like, what am I going to do with my life? Like that kind of thing. You guys, I'm sure, have experienced that. I knew that I was good at math. I knew that I was good at other things too. But math seemed to be sort of an affinity. And so, I mean, I hate to be so lame as to say I just prayed about it and sought out some wise counsel. There were some interesting moments. I know, like with my dad, who is a Christian and understands, he had said, hey, maybe you should get a degree in engineering so you have like a fallback, right? Or you could eventually be a teacher. And I felt so strongly called that I said, I understand that you're older and wiser and all those things, but I want to burn that bridge and go to school to just like specifically to be a teacher. Because I felt like, knowing my own character, that if I did have a way out, given the right or wrong set of circumstances, I would take that way out, and I didn't want to give myself that option. I mean, I always could go back to school for, I could force it for sure. But yeah, so like from, kind of from like it was like the spring semester of my 10th grade year, honestly praying and considering just saying, math teacher, okay. And then it was kind of like keep trying to push open doors until one gets slammed shut. And then in that case, maybe you do try to, find a different way. And so the doors kept on opening, and 20 whatever years later, here I am. So yeah. Everybody has their story. Mine does not involve like drug or alcohol abuse or extreme.
And then the Bible just landed on
Yeah, I mean, I like hearing those stories where someone like came out of some horrific situation, drug and murders and whatever, and they like have, found the straight and narrow. I mean, I don't know that Valor would hire me if I was like a convicted murderer or something. Like, I'm good now, Be like, why don't you find a different job? But I do love those stories. But yeah, I mean, for me, it was just kind of more of the, sincerely trying to see God and hearing nothing and for a while, and then kind of like, okay, I think I'm starting to hear something, and going for it. So yeah. Someday you guys will have your own stories along those lines, and I would love to hear them. It's fun to kind of reflect on where you've been. So yeah. Math is fun, but it's not life. Oh man, yeah. I mean, that's the truth. I do enjoy math, but when I go home, I do what I need to do, and I do enjoy like learning and discovering new things or remembering things. But I'd rather play with my kids. I mean, truth be told, it's like no contest. But whatever, it's all good. I enjoy. Well, I will say this: I enjoy working with you guys way more than I enjoy like the technicalities of the math. Right? I love to like watch you guys discuss and mess it up, and then get it right and figure it all out, and then I'm like, all right, good job, go do whatever you're gonna do, and it's kind of that's where I get my enjoyment, because the math hasn't changed in a while. Right? It's like kind of the same. But you guys are different than the folks I worked with last year, and the folks I hopefully get to work with next year will be different from you, and so that's kind of the fun thing for me. Okay, well, let's do one thing in here. This is actually going to work out pretty good. We'll probably just do one of these, and we'll break, and then we'll do our test tomorrow, and that'll be it. So this right here, we're back to this is something you got to know. This is like an AP topic now. So 8.3 and 8.4. Just for chapter 8 only. 8.5, back to, you got to know this, in May, in April, in whenever, right? You got to know this on, I think it's like May, it's kind of late this year, like May 15th or something. I don't know if you guys have seen the dates published, but the dates are a little bit later than normal. So anyway, here's the good news. I mean, I know, we talked about this before, I know when you turned over and you saw those words, partial fractions, like, your heart rate went from like 75 to 175. Your stress level was like, whoop.
I heard that's that one.
You just died. Somebody revived. You got revived already. Okay. So yeah, kind of scary sort of topic. But the good news is this. The AP exam will only use non-repeated, distinct, linear factor partial fractions. Also known as the easiest conceivable partial fractions. Like, they do not get any easier than this. Seriously.
Mr. Blake's are just
Yeah, no irreducible quadratics and all that stuff. Repeated linears, repeated quadratics.
Mr. Blake would be like, how did you do
Nothing like that.
I just kind of made one up.
So we're just going to keep it simple. Is that okay? You guys are all okay with keeping it sort of simple? So we're going to just do this. I'm not going to expand this. I mean, honestly, if you really had to, you could go back and refigure out all the partial fraction stuff and apply it. But I don't think that that's going to serve our time very well. So here's what you do. You split the fraction up using partial fraction methods, bless you, and then you integrate. Can I try to connect this? I would like to try to connect this for you guys with what we've done in the past and give you the broad perspective on why we're going to do this, because it might seem like you have options, but you really don't. Okay? So let's go through. You're happily taking your quiz. It's going well. Your test is going okay. You come up to this one right here, and you think, oh, it's a fraction, right? It's the integral of a fraction. So what should be your first question as you investigate?
Is it ln?
And is it ln? Yeah, it's really not even close because the derivative of the bottom is 2x minus 5. The top's only a 1. We're way, way, way off. So it's definitely not ln. If you try to flip up, wouldn't you get the to the negative 1 thing?
Yeah.
And that's not going to go very well. You very well could look at this and say, hey, I think this might be arcsine or arctan. And if it was going to be one of those two, which one would it have to be?
Arctan.
But it doesn't look like arctan, so what would we have to try? So let's try that real quick. Let's try complete the square and see what happens with this. I think you'll find a somewhat interesting result. So I will be, I don't know, maybe I should just write this and I'll erase it. Like if you want to try to squeeze this in, that's fine. I'm gonna write this and then erase it because this is not gonna work. But here's what you'd get. You'd write, yeah, it just doesn't work.
It doesn't work.
So you get x squared minus 5x. You group it.
Less than 1 and
So then the b is odd. So I mean that adds a layer of difficulty, but it doesn't make it impossible. So what you would do is you'd say negative 5 in half squared is,
2.5.
well, no, do 5 halves. It's easier.
Oh.
5 squared,
25.
25 fourths. Yeah, so what you do is you would add 25 fourths to the inside. And of course, you can't just do that unless you, on the outside, subtract. Yeah, so you subtract 25 fourths out here, and you think, hey, I think this is going to be arctan. So we go x minus 5 halves squared is how that would factor. And here's where it goes wrong. When you combine the 6 minus 25 fourths, isn't that really 24 fourths minus 25 fourths?
So the negative.
So it's negative. It's not arctan, because doesn't arctan have to be u squared plus a squared? And it's minus. So it just doesn't work, right? I mean, like you try to make it fit the arctangent pattern. Because the arctangent pattern is this. It's integral of u prime a over a squared plus u squared. And this would be your denominator based on completing the square. That's not a squared plus u squared. It's negative a squared plus u squared. And that one little detail of minus, kind of like the little detail of squared up here, is what makes it going from being an arctan to something else. Does that make sense? So you very well could run into something like this and think, hey, it's going to be an arctan complete the square. You might run through a few steps like this. As soon as you see that the thing you subtract from the outside is going to cause it to be a negative, it's not going to be arctan anymore. Make sense? So kind of tricky. But maybe that would be a thought process you'd have. I just wanted to kind of alert you to the fact that you might think it's one thing and then you get into it and you're like, oh, wait a minute, I'm off by a positive negative. It's something else is what that means. So here's how we do this. If it's not arcsine or arctan, then our final, and this, I promise this is the final technique for us this year, is the whole partial fraction decomposition. So here's how we go about that. We're going to factor it first. So it'd be 1 over, and how does that factor?
Minus 6,
X minus, no.
You get x minus 3 times x minus 2.
There you go. It's okay. I make mistakes like that too. It happens. Okay, so once you have factored it, you can see the two factors in the denominator. Here's how we would split this up. I would come over to the side, or you could do this down below. However you choose to format it is fine. I'm going to do it off to the side because this is just a little bit of algebra. Here's how you set it up. Remember the A and the B? This is not that bad. It really isn't. We'll clean this up pretty quick. So you're basically saying, you know, the fraction that I've got in there is equal to two fractions being added together. We just don't know what the numerators would be. So the way that we handle this is we clear out all the fractions, and we do that by multiplying by the least common multiple of all the denominators. So this would be a step, like once you kind of remember this, we'd probably skip this step real quick. Think about what's going to happen. If I multiply by that least common multiple, isn't everything going to cancel out on the first one? So I'm just left with 1, right? And on the second one, the a, of course, is left over. But wouldn't the x minus 3's cancel out when I did this? Leaving us with just an x minus 2. And then on the last one, The x minus 2's would cancel out, leaving us with an x minus 3. So what we do at this point is we think about, we want to figure out the a and the b, but we can't really do that as it stands. We need to make one of them go away. So here's how I usually note that. I'm going to say if x equals 2. It's supposed to be a 2. If x equals 2, which one goes away? A, right? Because 2 minus 2 is 0, so it'd just be a times 0. So if x equals 2, then 1 equals b times 2 minus 3 is negative 1. Therefore, b is negative 1. And then what would I need the x to be to figure out the a value? 3. Yep. So if x is 3, then 1 equals, look at that, 1 just equals a plus 0 technically, but 1 just equals a. So then we can go back and we can say, well, this really is the integral of, let's see here, it would be 1 over x minus 3 minus 1 over x minus 2 dx. Both of those are nice, beautiful natural logs. So you'd end up with natural log of x minus 3, absolute valued, minus natural log of x minus 2 plus c. One brief note for you. Do you guys remember if you are subtracting logs, you can condense them by using division? Yeah, so you might see an answer that looks like that. ln of the absolute value of x minus 3 over x minus 2. That is not an uncommon thing to see. So. Okay, so I wanted to get that in because I wanted to make sure that you weren't